Hello, and welcome to our module on uniform circular motion. We're going to talk about circular motion and rotational motion later on in the semester. This chapter, we're going to focus on circular motion that is uniform, and by that we mean constant. So moving at a constant rate. Our circle can be in a horizontal plane. So you could think about a merry-go-round that's moving in a constant way. So we're not talking about speeding it up or slowing it down. We're just going to be talking about if it was moving at a constant rate. Or it can be a vertical circle. So think about a Ferris wheel. Not while it's putting on riders and getting up to speed, but in that lovely moment on a Ferris wheel where you're already on it and it's just going at a constant rate. So those are kind of my two examples, conceptual examples of the circles that we'll be thinking about. Oh, I have one more. So we'll do a problem that involves circular motion with a ball on a string, and there are kind of two ways I can make this a circular motion. I can do it like that and have a horizontal plane, or I can do it like this and have it in a vertical plane. So we'll talk about both kinds, and when we do, we need some more equations. We need some more definitions. So the first one is angular displacement. Angular displacement is the arc length that has been traced out along a portion of a circle divided by the radius. So you probably had this before in a math class. Here's the picture you would have looked at where R is my radius, and you can see that delta S is just a portion of the circle, R and S need to be in the same units, so like meters or centimeters. And when you do that, they're going to cancel out, and your change in theta, or your angular displacement, is in radians. So radians are often called a placeholder unit. When they are multiplied by something else, they go away. And I'm going to show you that here in a moment. So just like we had linear displacement, delta x, we had linear displacement, we could take that, divide by time, and get velocity or speed if we're including direction. We're going to have a new quantity that we're defining as angular speed. Angular speed, this is a Greek letter omega. Lowercase is not a W. The angular speed is the angular displacement divided by the change in time. So this is going to tell us how fast something's going. The units that are the SI units for this thing is radians per second. But sometimes we'll see revolutions per second, and I'll show you how to get those into radians per second later. So angular speed is displacement, angular displacement divided by time. Let's go back to my turntable. I have taped two of my little flower chips to this. One is closer to the center of the circle, which would be my axis of rotation, and one is further away. So if I think about undergoing a rotation, can you compare the angular displacement of the green chip to the blue chip? Think about how you would compare the angular displacement. It's going to be the same, right? If one of them goes through 90 degrees, the other one goes through 90 degrees. They're going to have identical angular displacement. So what does that mean for the angular speed? Well, since angular speed is angular displacement divided by time, the two rotate through the same angular displacement in the same time. So the angular speeds are going to be the same. Is everything the same? No. If you've ever been on a merry-go-round that's going really fast and maybe you're like not feeling so good, what do? You walk towards the center of the merry-go-round because something feels like it's not as fast. What isn't as fast? The linear velocity, which we've seen before, but its relationship to the angular speed is we take the angular speed multiplied by r, where r is the distance to the axis of rotation, and that gives me my linear speed. Let's think about this again. The r for the green one is about half of the r for the blue one. So the blue one is going to be moving faster in a linear way, tangentially, moving faster than the green one. All right, so a word about units here. R, that's my distance to the axis of rotation from my object that's rotating. That's going to be a displacement, so like in meters. Angular speed, SI unit, radians per second. When I multiply those, I get meters per second because this is just a placeholder. The radians is just a placeholder unit. Because it's multiplied by meters, it goes away, and I have meters per second, which fits with what we know for linear speed. And again, this is going to be a tangential linear speed. It's an instantaneous speed that is tangent to the circle at that point. All right, so we did angular displacement, we did angular speed. What do you think is next? Centripetal acceleration. Centripetal acceleration is the linear speed squared divided by the distance to the axis of rotation. So thinking about my turntable with my green and my blue chips on them, the blue one had the bigger linear speed, so it will have the bigger centripetal acceleration. If I take centripetal acceleration and put it together with Newton's second law, if I substitute in for acceleration, the centripetal acceleration, I get this equation. If I then take my equation from the previous board, where I have the linear speed equal to the distance to the axis of rotation multiplied by the angular speed, put that in here, I get this, which reduces to this. So this and this are equations on your equation sheet, which we will start working some problems now.